Welcome to Compare WAN Connectivity Options. We are ready to move on to Domain 3 of the ENSLD blueprint, which is more focused on wide area networks. Domain 2 is all focused on campus infrastructures where we have high reliable, high bandwidth connections, and we can use those to build the optimal network designs. But when we're connecting out to remote sites and branch locations that might be across the world, we don't necessarily have the same connectivity options. So in this video series, we're going to unpack some of those options that we do have available to us, including things like service provider VPNs and Metro Ethernet, dark and lit fiber, even cellular connections these days. So come along with us as we unpack all of these different options, and with that, I will see you in the next video. When I think about traditional wide area network connectivity options, I tend to think about things like frame relay and T1s and E1s and other leased line applications. But this concept of leased line has really fallen out of favor within the service provider world for a variety of reasons, one of which is just inefficiency of traffic utilization and bandwidth on their backbone. So enter this concept of virtual private networks. I don't know about you, but when I think about VPN, I think about an encrypted tunnel across the internet, right, from maybe one of my sites to another site. And so this concept, though, is simply trying to virtually segment my traffic apart from other users' traffic. Well, that's the exact same concept we're going to see in service provider VPNs, because what they really want to do is take all of their customers and switch all of their customer traffic across a shared infrastructure. But if they're going to do that, and customer A and customer B are going to share the same, literally the same switch ports in some cases, going across the same trunk link as part of a packet switch infrastructure, well, in those cases, we need to make sure that we are segmenting the network traffic, hence VPN. In this video, we're going to explore not only what exactly it means to do this in a service provider network, but also find out what the common applications are, especially the differences between Layer 2 and Layer 3 VPN services. Let's dive in. Anytime we're using a service provider, we're going to have to assume that our traffic is entering in. Let's say we are customer A, and it's going to be sharing the same infrastructure as another service provider customer. Let's call them customer B. As my traffic propagates through the network, their traffic will also be propagating across the same network. And it is the responsibility of the service provider to make sure that the traffic, even though they're on the same infrastructure, none the two shall cross. We do not want customer A traffic showing up on the inside of customer B's network. Now, a lot of these privacy concerns are already taken care of in leased line technology. That's because we're carving out virtual circuits inside the service provider network that are going to separate the customer traffic. But as mentioned in the intro, the service providers are no longer interested in doing leased line applications. Instead, we want to take advantage of an Ethernet infrastructure. And if we're going to do that, then that means that we're switching raw Ethernet packets from customer A and customer B on the same infrastructure. And that can cause major problems. Again, we need to make sure that those customers cannot communicate with one another by accident. And this is where the concept of VPN comes into play, and there are two different categories of VPN services. The first of which is going to be Layer 2 VPN services. The goal of a Layer 2 VPN is probably just like it sounds. It's to extend Layer 2 connectivity out to remote sites. Specifically, if I'm going to connect a customer site into my service provider network, and on the other side I'm connecting to a remote site for that customer, then these two devices should be able to see each other at Layer 2. If they're seeing each other at Layer 2, then this should remind us of T1 and E1 connectivity, where I have a direct connection. I can form routing relationships with one another. So for example, I could run OSPF between these two routers. They would see each other as OSPF neighbors, they would exchange routes, and life would be good. Now, when we look at Layer 2 VPN technologies, there are two primary technologies we need to be aware of. The first is going to be the Virtual Private LAN Service, or VPLS. The key word for VPLS is going to be this one right here. It's really three words. It's Local Area Network, or LAN. We want to turn this cloud into a LAN by which we could connect a third site, let's say, and have all three of these routers form adjacencies with one another. At this point, we have logically placed all of our routers onto one Layer 2 domain. That means we can share an IP subnet. For example, we could have .1, .2, and .3 as IP addresses all on the same network. The second technology we have is the Virtual Private Wire Service, or VPWS. VPWS accomplishes the same thing as VPLS, except it is only point-to-point. Once again, we can look at the key word here. In this case, the W being wire means we're going to form one virtual wire between two locations. So in our example here, the purple sites, we could use VPWS to extend Layer 2 connectivity between them. And we can compare that to VPLS, where VPLS is a point-to-multipoint service, which, as we explained earlier, allows us to connect many routers to one Layer 2 domain. Interestingly, VPLS and VPWS both use the same underlying technology inside the service provider cloud, and that would be multi-protocol label switching, or MPLS. Now, even though we can use MPLS as the foundation to build VPLS and VPWS on, MPLS itself is going to enable layer 3 VPNs as a different option for us in the WAN connectivity space. The goal of a layer 3 VPN is, once again, probably how it sounds, is to establish layer 3 connectivity among our different locations. So let's say we have a couple of remote sites and we're going to connect our edge routers up to this service provider domain. In this case, we're going to call these customer edge routers, or CE routers. It's the router that receives the handoff from the service provider. But here's what's interesting is that when we think about this from a layer 3 perspective, this service provider space, again, being a layer 3 packet switched Ethernet infrastructure, we can no longer form a routing adjacency with one another because if we're going to do that, we need to be on the same network segment. We need to be on the same broadcast domain. And that is no longer the case in a layer 3 VPN. So how do we exchange our routes with one another if we can't form routing protocol adjacencies? Well, we do still need to run a routing protocol, but if we can't form an adjacency to my router on the other end, well, then I'm going to have to form a relationship with my upstream router. In this case, that would be the provider edge router, or PE device. In all of my locations, I'm going to have a PE router of some kind to which I not only attach for connectivity's sake, but I also run a routing protocol like BGP with it. At this point, let's say I have a bunch of routes, let's say networks A, B, and C, that maybe I've learned via a routing protocol downstream. Maybe I'm running OSPF, or maybe they're directly attached routes. Regardless of how I learn these routes, I'm going to inject them into the BGP domain. I'm going to share them with my provider edge router, and then the provider edge router will make sure that those routes get across its infrastructure to the other side, at which point that provider edge will share it downstream to the customer edge device. I remember when I first learned about MPLS and how service providers build these networks, I thought it was really strange that I'm sharing my routes with a service provider. I'm actually forming a routing adjacency with the service provider router. But that is how native MPLS works. Now, I could always build a VPN across MPLS if I really wanted to. I could encapsulate my traffic and then form direct routing relationships with one another that way. But this can be really cumbersome outside of the software-defined wide area networking world, or SD-WAN. One of the solutions SD-WAN brings to the table is solving this issue of sharing, call it too much information with the service provider. I mean, do I really want to share all of my routes with the service provider? Am I comfortable with the service provider knowing my routes and making sure that they don't accidentally give my route maybe to a different customer? Because that would be really bad if I'm sharing routes with somebody who isn't one of my locations. So we can always consider an overlay VPN, and especially if we're running SD-WAN, that's absolutely what we're going to do to maximize my security. But outside of that space, we are going to have to trust the service provider to keep our routes and our network traffic properly segmented. So, as for our key takeaways here, first of all, service provider VPNs are intended to allow them to build their infrastructure on layer 3 Ethernet, and then from there they can extend layer 2 or layer 3 services to us. For example, on the layer 2 side, we saw VPLS, which essentially forms a logical layer 2 connection to many different locations, as well as VPWS, which is a point-to-point version of VPLS. Next, we took a look at layer 3 VPNs, and with layer 3 VPNs, we can't form direct routing relationships with the routers that are at our remote sites. Instead, we have to form routing relationships to the service provider and hope that they keep our network traffic and route segmented, and again, they're very good at that. But if for any reason we have trust issues in that relationship, then we might want to build an overlay, and we could think of a VPN, but especially we're going to look at SD-WAN in those cases. I hope this has been informative for you. I'd like to thank you for viewing. We spent a lot of time talking about local area networks or LANs and wide area networks or WANs. But what about these metropolitan area networks or MANs? In this video, we're going to explore two different types of metropolitan networks that we can build that essentially function as a wide area network to us. Let's take a look. First, let's talk about Metro Ethernet, which is sometimes referred to as Metro E. Metro Ethernet, as the name implies, is intent on not only handing Ethernet off to the customer, but also building our infrastructure on Ethernet. This simplifies the topology and makes it extremely flexible from a service provider perspective. By leveraging Metro E, we can hand off Ethernet to each of our customer sites. And furthermore, we're able to extend layer 2 across our infrastructure. This should remind us of VPWS that we just talked about in this topology here, we have a point-to-point layer 2 connection between our two sites. However, Metro Ethernet also allows us to extend to multiple sites. So not only point-to-point connections, like in the case that we drew here, but also point-to-multipoint connections, which should remind us of VPLS. From a customer perspective, we would probably put our own layer 3 devices at each location, and that way we can form direct routing relationships to one another. Let's say by running OSPF or EIGRP and such. But despite the similarities to VPLS and VPWS, the infrastructure from a service provider perspective, this is going to be a whole lot different when we're running Metro Ethernet. Furthermore, because of how we build this infrastructure, in a lot of cases, the service provider is able to increase the bandwidth at any time. So not only can we scale out to multiple sites via this point-to-multipoint connectivity, but we can also increase the scale of our bandwidth on an as-needed basis. Let's say that here on the bottom, we turn up this circuit and we pay our service provider for 500 megabits per second to be delivered to us. But then as business grows, we realize that we need a whole lot more bandwidth. And so we call our service provider up, and usually on the phone via configuration, they're able to increase this to, let's say, a gig or more. And in most cases, they can do this again via configuration. They won't have to come out and rip and replace any of the equipment that they've already installed. Now, yes, we are talking about gigabit speeds between our network locations. And that's a sharp increase compared to some of the wide area networking technologies that we've already discussed. Metro Ethernet, SONET, and SDH all qualify as Metropolitan Area Networks, or MANs. In a lot of ways, the MAN is a balance between LAN and WAN technologies. For example, WAN technologies are built with distance in mind. We want to connect our remote sites. But from a LAN perspective, we don't really do distance. We like to stay inside of a building. Well, a MAN can bridge that gap. We're able to connect to sites that are further away, but we've drawn here lots of buildings and such. That's because a metropolitan area network is intended to be built within the metropolitan area. It's why it's part of its name. A metropolitan area is usually a city or maybe cities around a city. And so we might be able to extend across town, let's say, or maybe even to, again, a neighboring city, but we wouldn't be able to connect across a country using a metropolitan area network technology. Now, one of the strengths of local area networks is bandwidth and performance and resiliency. And the WAN, not so much. Its specialty isn't delivering high amounts of bandwidth to our sites. Its specialty is connecting our sites, period. And so metropolitan area networks, again, they bridge that gap. We're able to deliver gigabit or more, maybe even up to 40 gig, depending on the technology that we're deploying with a metropolitan area network. I mean, yeah, LANs can get up to 100 gig, and that's great, and they'll always support more bandwidth and have higher resiliency. But hey, 40 gig on a metropolitan area network is nothing to sneeze at, because in most cases, our WAN service providers aren't able to deliver much more than a gig to us at any of our locations. In a lot of cases, it's way less than a gig as well. Next, let's look at SONET and SDH, which is a different type of metropolitan area network technology. SONET, or Synchronous Optical Networking, is built and maintained by ANSI, which is the American National Standards Institute. It has the word American in it, and so as you can imagine, SONET is built for the US and Canada. Meanwhile, Synchronous Data Hierarchy, or SDH, is maintained by the International Telecommunications Union, or ITU. And that is for pretty much everywhere else. SONET and SDH are two sides of the same coin. They are very similar technologies. They are just used in different regions throughout the world. This should sound really familiar because when we think about it, we have a similar situation with T1s versus E1s. They're very similar technologies and they deliver very similar amounts of bandwidth, but they're slightly different and deployed to different regions. Now, both SONET and SDH are built with resiliency in mind. And specifically, when we're going to connect multiple sites, we always build it in a ring topology. This is why if you've ever heard SONET and SDH talked about, oftentimes we call them SONET rings or SDH rings. In fact, even if we're extending out to a single site, out here let's say, we still have to build this in a ring topology. Now ideally this is a physical, in other words a geographical ring, meaning that we send this one north, for example, and this one south, but unfortunately that's not always the case. We wouldn't want, for example, to run fiber two different directions and then bring them together and run it through the same conduit underground and then call that a ring. Because if we take out this one spot right here, then we lose both sides of our ring, and it's not really as resilient as it sounds when we're talking about redundancy across a ring topology. So it's a question to ask when we're doing our designs and selecting our service providers is for them to identify the geographical or physical layout of these different fiber rings that they're running. Now, as you can imagine from that conversation, SONET and SDH have a focus on resiliency. Not only do we have these rings in place, but we have the ability to fail over very quickly. If, for example, our traffic is going this way on this ring and this link goes down, we can fail over to the other side within milliseconds. This is a far superior approach to, let's say, Ethernet. If those of us who are Ethernet engineers are looking at this and panicking because we see a loop, and so we're already thinking about spanning tree protocol from a layer 2 perspective, and SONET and SDH, they don't require those because there's no such thing as a broadcast loop in these technologies. Now, SONET and SDH are often delivered as a circuit type to a customer, and that circuit type is usually equated with a particular bandwidth level. Now, when it comes to SONET versus SDH, we do use different words from different specifications for the different protocols. However, the speeds are usually the same. For example, SONET, unfortunately, has two different words we have to learn, STS and OC. And so, for example, SONET has an STS1, otherwise known as an OC1 type of circuit, and that's going to deliver 51.84 megabits per second. Meanwhile, SDH has something similar. SDH, however, calls it an STM. And in this case, the 51.84 megabits per second aligns with STM-0 service. So even though the bandwidth is the same, we have to understand that on one side with SONET, it's STS1, and on the SDH side, it's STM0. Now 51 meg is already pretty good from a WAN perspective. However, we can definitely crank that up very significantly. As mentioned earlier, we can get up to nearly 40 gigs, specifically 39.81 gigabits per second. On the SONET side, we call this STS-768 or OC-768. Meanwhile, on the SDH side, we call this STM-256. Now 40 gig is not the finish line for SONET or SDH. In fact, they have standards in place right now they're working on that's going to take the standard to 100 gig and beyond. Keep in mind, from this conversation's perspective, the goal is not necessarily for us to sit down and memorize every service level that we can get out of SONET and SDH. The purpose of this is to understand the architecture that's at play and what we can accomplish with it. And one thing service providers love to accomplish with this is to run Metro Ethernet over SONET and SDH. Keep in mind, SONET SDH, this is not an Ethernet-based protocol. As mentioned, we are looping from a layer 2 perspective around running a very different protocol from Ethernet. Now from a traditional perspective, that's fine. We can strip the Ethernet header off and still forward the IP packet across the SONET infrastructure. However, there's nothing saying we can't encapsulate the Ethernet header as well. At that point, we can actually run Metro Ethernet over SONET and SDH, taking advantage of all the resiliency and robustness of a SONET SDH ring, while deploying the advantages of Metro Ethernet by delivering Ethernet handoffs and giving us flexibility in our configurations by deploying that kind of infrastructure. So within the context of ENSLD, here's what we need to keep in mind with this conversation. First of all, metropolitan area networks, or MANs, they fall in between LANs and WANs. We have some of the advantages in the resiliency and the bandwidth of local area networks, and we can't quite go as far as wide area networks, but we still want to extend between our branches. Meanwhile, Metro Ethernet is one of those options of technology we can deploy as a metropolitan area network. It's a flexible protocol. It allows us to deliver Ethernet as handoffs to the customer, but it also extends layer 2, so it should be pretty reminiscent of VPLS and VPWS as far as how we can connect our branches together. Lastly, from a SONET SDH perspective, they're very similar protocols. They are region locked, so to speak, so SONET's really in the US and Canada, and SDH is pretty much everywhere else, and we see a lot of similarities between them, but understand that they can scale up to 40 gig. So we can get a whole lot of bandwidth out of these protocols. It's not really just about delivering a gig or 10 gig. We can deliver massive bandwidth across a metropolitan area by leveraging these technologies. And on top of that, we can even deploy Metro Ethernet on top of SONET and SDH. That is certainly an option that service providers have available to them in this space. I hope this has been informative for you. I'd like to thank you for viewing. Now, at first glance, we might say, well, okay, dark and lit fiber. Dark fiber is not very useful for us because optics require light, and so lit fiber is going to be the way we go, right? Well, believe it or not, there are two different choices for us when it comes to fiber selection. We could have dark fiber or lit fiber. In this video, we're going to explore the difference between these and when we might want to use one over the other. Let's take a look. When I have a site and I need to connect that site to a different site, and I'm going to connect it via fiber, the question is whether that fiber has already been lit or not. In other words, if I have fiber between two of my sites, and I'm going to put an optic on one end and an optic on the other end, and we're going to communicate back and forth between these two locations, well, this would be a dark fiber service. And the reason we call it dark is because the fiber itself was dark before I connected to it. If I'm going to use dark fiber, I need to provide my own optics on both ends of the link. Furthermore, somehow I need to get my hands on this fiber. And there are two primary ways of doing that. For one, I could simply own my own fiber. If this is between two buildings on my own campus, I could hire a company to come out and dig fiber between the two buildings. At that point, I own the fiber and I can do whatever I want with it. However, if I'm going across public land or across the city or something along those lines, then I'm probably going to have to find somebody who's already put fiber in the ground, and at that point I would be leasing this dark fiber connection. So when we think about this, dark fiber applications are pretty limited, either to our own campus or maybe across the city. So what is a lit fiber service then? Well, a lit fiber service involves a service provider that deploys their own devices on either end of the fiber. So they are going to deploy their own optics, they're going to take care of this connection, and from there they're going to hand off to other companies. Their goal here is for them to maximize the connection of this link by selling bandwidth to other organizations. So let's say I'm one of those organizations, and I've got my router on both sides of this connection again, and I'm going to pay them so much money a month for them to connect me to their lit fiber. In a lot of cases, this could be a copper connection. I could truly connect via copper to a lit fiber service. Because again, they have already lit that fiber and now they're simply handing off parts of that connection. For example, let's say they activate a 10 gig connection between their two devices. They might sell me 1 gig of throughput, but then to another customer, they might sell 2 gigs of throughput. So in most cases involving lit fiber services, that fiber belongs not just to me, but to everyone else that service provider is connecting on it. So we can see the advantages and disadvantages to each one of these situations. The advantage to dark fiber is that we are in total control of this connection. I could not only deploy 10 gig optics, I could deploy 40 or even 100 gig optics onto each end of this fiber. The downside to this, of course, is that I have to pay for those optics. And 100 gig optics are not cheap. Neither are 40 gig and neither are 10 gig when we have to cross great distances. Furthermore, the availability of this solution is going to be low. Because again, I either need to already own that fiber or I need to lease it from somebody. And it's not always available for me to lease it if the fiber is just not available. Now the advantage of lit fiber service kind of flips this around. Because now we don't have to worry about purchasing optics, for example. We can let the service provider handle that. And the availability of this solution is going to be pretty good. However, the downside is I'm going to pay a whole lot more money per month for less bandwidth. For example, I might only get 1 gig of throughput on this fiber connection, and I'm going to be paying monthly to maintain it. Compare that with dark fiber, where if I own the dark fiber, there is no monthly cost to running this. If I have to lease it, then there will be a monthly cost, but it's probably not going to be as high as the lit fiber service would have been. And the other issue comes back to control. I can't control the latency of this link as well, for example. I can't control the bandwidth as easily. If I go back to them and say, hey, I need another 5 gig of throughput on this, well, maybe they've already oversubscribed the link, and there's no way for them to deliver 5 gig on that connection. So, as is often the case with these scenarios, we have two different options and neither one is perfect. Instead, it is our job as network designers to come in and evaluate a dark fiber solution versus a lit fiber solution, taking a look at the advantages and disadvantages of both and comparing those to the situational needs. Now, as part of this conversation, we need to talk a little bit about how we can possibly light fiber connections. If we are spinning up a dark fiber service and connecting two of our sites, let's say, then again, we need to purchase the optics in order to make this happen. So what are our options and what should we be doing in this space? Well, the first thing to know is that fiber that exists outside of a building, in other words, between locations, this is going to be single mode fiber. Single mode fiber is built with distance in mind, and indeed that's what we're going to have to cover when we're doing our designs. Specifically, we need to look at different optics based on distance. How far are we going? Because the further distance we have to go, the more expensive the optics that we're going to have to purchase. For example, Cisco makes a 100 gig optic that can go up to 40 kilometers away, which is an incredible distance, but I can tell you right now that that optic is not cheap. Meanwhile, Cisco also makes 10 gig optics that can achieve up to 80 kilometers distance. So one of the first steps in our design process is going to be looking at the distance between our connections and then deciding which transceiver to purchase as part of that. Now, traditional fiber optics are only going to give us one single logical connection. It makes sense, right? We're transmitting on one side, receiving on the other, and vice versa. We're transmitting on the other side and receiving on the other. However, there does exist a technology that can place multiple connections onto a single fiber strand. And that technology is called dense wave division multiplexing, or DWDM. DWDM, in most cases, is going to be leveraged by service providers because we want to maximize the number of connections we can make on a single pair of fiber. The way DWDM works is, in a lot of ways, the same way wireless works. We divide different connections into different wavelengths, and different wavelengths effectively equate to different channels. As long as the wavelengths are different enough, these channels will not interfere with one another. So we could communicate on one channel that has a longer wavelength, a shorter frequency, and then we could communicate on a different channel that has a higher frequency and a shorter wavelength. And these two channels will not interfere with one another on the same line. So we can deploy DWDM optics onto each end of this fiber pair, and we can use these to communicate with up to 160 different channels depending on the channel size. Now, in a lot of cases, those channels are going to be reduced to 96 or 80 because we'll favor larger channel sizes, but the point remains that we can fit a lot of different logical connections onto a single fiber pair. As you can imagine, these transceivers are a little bit more expensive than our single mode transceivers, but at the same time, they're very valuable, especially to service providers. Incidentally, DWDM technology evolved from coarse wave division multiplexing, or CWDM. CWDM only supported up to 18 channels, which is still a lot, but nowhere near what we can achieve with DWDM. So in the end, if we're making decisions as to which transceivers we should use, if we're not a service provider, we're just lighting our own fiber for our own business's sake, then probably a single mode connection is all we're going to need. And again, at that point, we take a look at the distance as well as the bandwidth that we require on that link. If, however, we are a service provider and we need to have as many connections as possible to maximize the use of our fiber pair, then DWDM is absolutely something that we're going to want to consider. So when we're considering our fiber services, first of all, we have dark fiber. Dark fiber is dark to us, meaning that we have to not only have access to it via purchase or lease, but we also have to light it ourselves. We have to purchase our own optics for that connection. Meanwhile, we could go with a lit fiber service. So the lit fiber service, the service provider lights the fiber and they hand it off to us, maybe via copper, maybe via fiber. But either way, we're going to be sharing that connection with other customers because it is a service that's being provided to us. Lastly, when it comes to how we want to light our fiber, if we're just lighting it for ourselves, for our own organization, we'd probably want to light it via single mode connections. And we remember that Cisco can support up to 40 and 80 kilometers depending on the optics that we choose. If, however, we're a service provider and we were going to build as many connections as possible across a single pair of fiber, then we would going to consider dense wave division multiplexing, or DWDM, because that can support up to 160 channels per connection, and that's going to really enable us to share that connection with as many customers as possible. I hope this has been informative for you, and I'd like to thank you for viewing. I know what you're thinking. All right, Jeff, I already understand cellular technology. I get it. 4G is fast. 5G is faster. What more do I need to know about it in order to be a good network designer? And the answer, admittedly, is not that much more than that. But at the same time, we do still need to know more than simply 4G and 5G. In this video, we're going to explore cellular technology, unpacking it a little bit more than maybe we traditionally do in a networking role, and then also how we incorporate cellular connections into our designs. Let's dive in. 3G and 4G and 5G, these are all cellular terms that we understand because a lot of us are phone users. We have phones that we have connected out. We're paying for these services, or our companies are paying for them in some cases. But either way, we kind of understand that 3G is where we first got internet access and it has a low data rate. And 4G is where most of us are, at least at the time of this video, because 5G is still getting rolled out. But while 4G was faster than 3G, 5G is going to be faster than 4G. But by using these terms, for example, 5G, it's like saying Wi-Fi 6. Wi-Fi 6 is the new way that we have of numbering our Wi-Fis, right? We have Wi-Fi 4, Wi-Fi 5, Wi-Fi 6. But really, there's technology under the hood. And a lot of us networking engineers understand that Wi-Fi 6 is really 802.11ax. But because we're on the network and we're doing things like Wi-Fi instead of cellular, unless we have dedicated cellular experience, we might not necessarily know how the technologies work underneath the hood. For example, in the 3G world, we actually had two different technologies that were competing standards. We had Code Division Multiple Access, or CDMA, and this was primarily used in the US. But then we also had the Global System for Mobile Communications, or GSM, which found its home in Europe and other regions. But these two technologies are like Bluetooth and Wi-Fi. I mean, they couldn't be more different, and you can't take one set of hardware and support the other. So a phone that supports CDMA couldn't be carried over to a GSM network and vice versa. But while this caused a lot of problems, believe it or not, 4G had the same solution. On the one hand, we have LTE, a phrase that most of us are probably familiar with because a lot of our phones will tell us that we're on LTE, and we equate LTE with 4G. Well, LTE stands for long-term evolution, and it was designed to do just that, to evolve over time. But there was a competing standard at the start called WiMAX. WiMAX was designed to deliver 4G communications as well, just in a different way than LTE. And while we could have had the same situation as 3G, where we had two competing standards over the lifetime of this generation, fortunately very early on, WiMAX fell out of favor and LTE really won the day. We go back and forth in technology. Sometimes it's good to have competition, but other times it's good if we just all get behind one standard. And fortunately, that's what we did with LTE. Now, while CDMA and GSM, these were in the kilobits per second range of throughput, LTE was able very early on to deliver 300 megabits per second to our devices. Now, this isn't real-world application. You're probably not going to step outside of your house and get 300 meg down to your 4G phone, but at the same time, this is what it's capable of from a technology perspective. But as its name implied, we continued to evolve. And next we came out with LTE Advanced, which was backwards compatible with LTE phones, but also allowed for up to 600 meg of communication. And from there we evolved it again, and now we have LTE Advanced Pro, which is capable of roughly a gigabit of throughput. Now, I don't know about you, but when I look at my home internet service is roughly 100 meg. And that's phenomenal, and it's screaming fast. And so when we start to see these bandwidths climb up towards a gig, well, all of a sudden as a network engineer, we should probably start considering this as a viable option for us in reaching out to our remote sites, which is exactly the home that cellular connections is going to land for us. Now first, let's finish our cellular conversation. And so from a 5G perspective, what exactly are we hitting? Well, the theoretical max out of the gate for 5G is roughly 20 gig. That's, again, just absolutely incredible and mind-boggling that I could turn off my home internet and just rely on cellular communications for my needs. Now, that said, let's bring ourselves down to earth just a little bit here, because in the US, the average throughput for 4G is a whole lot closer to 30 meg. Now, again, this is a national average, so users in cities might see closer to the 300 or 600 meg of potential throughput, whereas users out in rural areas are going to see a whole lot less than 30 meg. So it balances it out, but at the same time, we understand that this isn't necessarily going to get us anywhere near a gig, but at the same time, even 30 meg is pretty good. Now, 5G is very early in its rollout, and different carriers are rolling it out in different ways, and so there's not a super fair way of evaluating 5G speeds, but right now, we can basically assume that we're going to get twice the speeds as 4G. Now, as good as this is, even being twice as good, it's probably going to get even better, because as it gets rolled out and properly deployed, we're going to see bandwidth increases similar to what we saw in the 4G space. Okay, so after all of that, we can finally take our cellular hats off and put our networking hats back on. How exactly does this help us with network designs? Well, we already mentioned it earlier, and that is that we can use cellular connections to connect our remote sites. We can plug Cisco cellular modules into the routers, and now the routers can become part of the cellular network. Once they're part of the cellular network, we can build a VPN between the two sites across this public domain. Now, traditionally, this has been primarily as a backup role. Cellular connections have not always been the most reliable, nor do they give as much throughput as some other technologies. However, if we're talking about in the 30 megabit per second space and possibly even up to the 300 meg or a gig, well, all of a sudden, we might evolve our thinking from backups to being the primary circuit. Now, while this is absolutely possible and should be considered in our network designs, we also need to take a couple of precautions. First of all, if we're going to consider it as part of the primary connection, we're going to want to make sure that we conduct a site survey. This means actually going to the site, and we'll want to take with us equipment that can tell us how strong that signal is in that location. The signal strength is going to determine whether we're closer to 300 meg, for example, or 30 meg, or hey, if it's really out in a rural area, well, it might be a whole lot less than 30 meg, and that might not meet our needs. Furthermore, consider the fact that metro areas are traditionally going to have much better wireless coverage. It's not a whole lot different than traditional WAN technologies. For example, in metro areas, traditionally, way back in the day, we could get DS3s, whereas out in rural areas, we can only get DS1s or T1s and E1s and such. And so we've always had better options available to us in metro spaces, and cellular connections aren't going to be any different there. And the last thing to consider is simply the fact that 4G is going to have better coverage than 5G. We always want to look at the speeds and say, wow, look how fast 5G is. But before we go investing money into a 5G solution, it might make sense for us to explore 4G. 4G is going to be a whole lot more cost effective and potentially deliver the speeds that we need anyways. So let's not fall into the trap of signing up for the latest and greatest technology when really the last generation of technology would be the better solution. So as we've seen from this conversation, cellular technology, just like networking technology, it doesn't stand still. We've evolved from 3G to 4G and 5G, and while most of us are familiar with that terminology, now we understand a little bit better of what exactly that means. Second of all, in most cases, cellular technology can be used as a backup connection. We don't necessarily need the fastest 5G or even the fastest 4G speeds to be backup. In most cases, just having access to the site in a downtime situation involving our primary WAN link is going to be good enough to go across the cellular connection. But third, as we've seen with the way 4G has evolved and with what 5G is capable of, we can start considering this as our primary circuit. And it depends on the location. We want to make sure, again, do that site survey, find out, do we have good enough coverage for this? But I mean, if on paper things are looking good and our site survey confirms that we're going to have good throughput, then there's no reason why we couldn't consider that as part of a full network design as our primary circuits. I hope this has been informative for you, and I'd like to thank you for viewing. If you're tracking the blueprint with me, then you'll see that as we come to the end of section 3.1, Cisco lays out SD-WAN Customer Edge. What exactly is that all about? And the interesting thing is that we're actually going to cover in a lot more detail all of the components of Cisco SD-WAN later on in this domain. So within domain 3, Cisco wants us to understand SD-WAN in greater detail. So in this video, we're going to explore some of the, I suppose, overview concepts of SD-WAN, specifically, again, in the blueprint they call out Customer Edge. So we're going to take a look at the Customer Edge and make sure that we understand that as it relates to the conversation around WAN connectivity. Let's take a look. So far, we spent a lot of time talking about what this WAN might look like, whether it's a layer 2 or layer 3 VPN like MPLS or dark fiber or cellular. But then at some point, we have to connect this into our actual network. some kind of device that's going to sit at the edge of our network relative to the WAN cloud and connect us to the edge of the other side of our network. This phrase, customer edge, is meaningful in the WAN space because we actually refer to this as a CE device, where CE means customer edge. Oftentimes that's going to connect directly to a device that's deployed by the WAN service provider, and we call that the provider edge or PE device. Now when it comes to Cisco hardware, in a lot of cases we're going to specify an integrated services router or maybe an aggregation services router, so an ISR or an ASR. Or Cisco just released the new Catalyst 8000s. Catalyst 8000s sound like switches, but they are in fact routers. Though if you look at the datasheet, Cisco refers to them as edge platforms. And that's simply because they have a lot of the functionality of ISRs and ASRs, and they just needed a new way of describing this particular family of products. Now, as we build out our understanding of how wide area networks come together, at some point we are going to need to tackle the concept of software-defined wide area networks, or SD-WAN. SD-WAN is the software-defined networking solution for the WAN space. And this isn't a Cisco-only conversation. Plenty of other vendors have SD-WAN solutions, and Cisco's product is called Cisco SD-WAN. Yeah, it's not the most clever name, I suppose, but Cisco actually did have a product that they called iWAN. It was designed to be an SD-WAN product that would compete with all of the new vendors that are showing up with all of these great new flashy products in the SD-WAN space. Unfortunately for Cisco, iWAN didn't pan out, and they had to go out and acquire one of those competitors that was giving them some grief. And the competitor that they acquired is none other than Viptela. Once they acquired Viptela and brought it into the Cisco solution, this is when it got rebranded as Cisco SD-WAN. Since iWAN had already been taken, I suppose that was their cute and clever name that they'd come up with for SD-WAN. They just decided to go with the little more straightforward product name like Cisco SD-WAN in the end. Now, when they acquired Viptela, it created a little bit of an interesting scenario for some Cisco customers. Because as Cisco customers, we love to deploy the ISRs and the ASRs, and now the 8000s to our network edges. However, these devices didn't originally have the SD-WAN feature set. In order to gain access to the SD-WAN feature set that Cisco is now selling, we had to purchase Viptela hardware. And yes, Viptela made hardware routers. They made software routers, actually, virtual routers. And specifically, we call these V-edges, where the little V stands for Viptela. Cisco actually still sells V-edges, at least at the time of this video. However, they have started migrating a lot of these products to end of sale. Now, these product lines are specifically going to be the V-Edge 100s, which are for small, medium businesses. They'll have a lot of integrated features, like they have a 100M, for example, with built-in mobile communications, and they had a 100MW that had built-in mobile and Wi-Fi services as well. But then they had larger, more robust platforms, like the V-Edge 1000, the V-Edge 2000, and the V-Edge 5000, which had 10 gig ports on it, for example. And as mentioned, they had a virtual V-Edge. They called that the V-Edge Cloud. So it's quite a portfolio that they acquired from Viptela, but again, we are Cisco users. We want to use Cisco platforms. And so Cisco knew this and planned to migrate all of the functionality of V-Edges into their existing portfolio. And as of today, that is what they have done. As such, we now use the C-Edges, the little C standing for Cisco, and built on familiar hardware, specifically the ISR 1000s and the ISR 4000s, not to mention the ASR 1000s. All of these are going to be able to be converted into a C-Edge device. Incidentally, the Catalyst 8000s were built for this, so they are supporting SD-WAN out the gate. But originally, these ISRs and these ASRs, they're running a version of iOS XE that doesn't know anything about SD-WAN. And so the way Cisco originally decided to handle this was to have two versions of iOS XE. They had a version that was built exclusively for SD-WAN, and they had a version that was built for traditional iOS functionality. And when we were deploying the router, we had to decide which of these software platforms to deploy. Well, fortunately nowadays, they took the SD-WAN and the iOS functionality and combined them into one single version of iOS XE. So I still deploy my one version of software onto my hardware, and now I get to select which mode of operation that I want. However, keep in mind that we are not simply logging into an iOS router and configuring it for SD-WAN. Once we decide to spin up an SD-WAN mode, it's going to run a very different feature set than the iOS version. And so functionally, it's still very similar to how it was when we had two different software products that we had to manage, but it's still better to have one version of code and simply flip a switch when we're ready to migrate maybe to SD-WAN. So the fundamental point we need to understand here is that Cisco did have this V-Edge platform that they acquired from Viptela, but if we're going to go out today and purchase brand new SD-WAN equipment, we're not going to want to purchase V-Edges. Cisco does, again, still have them available, but those are primarily for customers who have already significantly invested into the V-Edge platform and want to continue to grow their SD-WAN architecture on the V-Edge platform. Instead, if we are migrating to Cisco SD-WAN or otherwise plan to one day migrate to Cisco SD-WAN, then the C edge is the way to go, which ultimately means nothing much has changed because as Cisco customers, again, we were probably still looking at ISRs and ASRs. The biggest change for us is that these Catalyst 8000s now exist, and we'll want to consider those instead of potentially the ISR or ASR we're accustomed to acquiring. So as we look at this, we first of all need to keep in mind that when it comes to Cisco's SD-WAN solution, it is a platform that they call Cisco SD-WAN. Again, that came from an acquisition of Viptela, and when we look at the hardware that Cisco offers, we start with this concept of a V-Edge. The V-Edge was the routing platform, hardware and software, that came through the Viptela acquisition. However, nowadays we can support the C-Edges by deploying traditional platforms like ISRs and ASRs, or potentially the new Catalyst 8000s. Either way, we're able to support Cisco SD-WAN software on actual Cisco hardware, which is good. Now lastly, when we think about that software image, by the way, the software image is we have one software image that has two different modes of operation. So regardless of whether we're going to run in SD-WAN or non-SD-WAN operation, we still download that code to our ASR, ISR, Cat 8000, whatever it is, and we decide which mode of operation to run in, understanding that the two modes of operation are very, very different, and configuration is not going to migrate between the two, for example. So we can migrate to SD-WAN when we're ready for it. In the meantime, we will just simply run as we usually do on traditional iOS XE. I hope this has been informative for you, and I'd like to thank you for viewing. We have finished this skill, which means it's time to review what we've learned by taking a quiz. First up, out of 5 questions, which VPN provider options are able to connect many remote sites in point-to-multipoint fashion? Well, T1s and E1s, these are kind of a legacy format at this point, but we still use them in regular networking, and that's point-to-point only. VPLS is absolutely point-to-multipoint. Not only is it point-to-multipoint, but it is also layer 2. VPWS is point-to-point, so that's out. And MPLS is point-to-multipoint, and this would be at layer 3. So really, we want point-to-multipoint solutions. At this point, we're going to see a lot of service providers coming to us with MPLS and VPLS design options. And a lot of it's just going to come down to whether we want layer 2 or layer 3 connectivity. Next up, Metro Ethernet, SONET, and SDH are all examples of what type of network infrastructure? Well, given we're talking about WAN options, you'd think that the answer might be A. But more accurately, Metro Ethernet, SONET, and SDH are all part of a Metropolitan Area Network, or MAN. We spend a whole lot more time in our careers talking about WANs and LANs and maybe WLANs down here, but less so about personal area networks, or PANs, Bluetooth we think of, and then Metropolitan Area Networks as well. We recall that MANs fall between WANs and LANs in a lot of ways. They have a lot of bandwidth and reliability that LANs provide, but they can't quite go as far as what WANs are able to give us. So ultimately, D here is our answer. Question 3. In which type of WAN service is a customer always responsible for providing optical transceivers? The only answer here that makes sense would be dark fiber. We recall that dark fiber is when we are given the end of a fiber connection and we have to light it ourselves. Now with any of these other solutions, the provider is going to have some kind of equipment that they're going to pass a handoff off to us. In some cases this might be optical, and if it is optical, then yes, we will still have to provide an optic in order to connect to it. However, they might also hand off a copper connection. And if they hand off a copper connection, then we can plug that into any old switch we want. And that is why A is our answer. Next question. When using cellular as a WAN circuit, 5G is good for primary connections and 4G is only good for backups. True or false? Well, the reality is that we can be considering cellular connections as our primary WAN circuits. And yes, 5G connections look really, really good. When we talk about theoretical maxes of 20 gig, that sounds amazing. But when we back that up and look at 4G technology, we know that 4G maxes out, at least at the time of this video, at roughly a gigabit of throughput as a theoretical max. However, we also recall that we can't get nearly a gig, just like we can't get nearly 20 gig on 5G today, we can't get nearly a gig on 4G, and the reality is that in the US, the average consumption at 4G is going to be around 30 meg. Now, you and I might look at 30 meg and interpret that very differently. For some sites, that would be a fantastic primary connection. For other sites, it's going to be nowhere near good enough to be a primary connection. But a lot of this isn't just the bandwidth, it's also the reliability. And the reliability of 4G is actually better than 5G in most places in the world today. Long story short, the answer here is false, because we can use 4G for primary connections in some cases. If the reliability of the signal is good, and if the bandwidth we're getting is sufficient, then by all rights, we can use that as our primary connections. Last question. Which Cisco platforms are able to be converted into C-edges in an SD-WAN deployment? This is going to require a little bit of memorization, but that's fair game on the ENSLD for them to ask a question like this. So when we look, all of these platforms show up in Cisco's portfolio, but not all of them support SD-WAN. Specifically, the ASR 9000s are built for service providers and they won't support SD-WAN. Neither do, by the way, the Catalyst 9000s. Those are primarily switches. Technically, there's some wireless LAN controllers and access points in there as well. But we will recall from our conversation that the ISR 1000s, 4000s, and the ASR 1000s, along with the new Catalyst 8000s, these are going to be our platforms of choice when it comes to SD-WAN. Well, that wraps up this quiz. If you found yourself lacking any of this information, then be sure to go back and watch the appropriate videos in order to make sure we've got it all locked down. Otherwise, congratulations on completing Compare WAN Connectivity Options. I hope this has been informative for you. I'd like to thank you for viewing.